We are somewhere in the middle of this lecture series, lecture number 6, about the converter modeling. The subject of this lecture is DCM PWM switch model and its application and implication. In the previous lecture, we evaluate the small signal characteristic of PWM switch, and we derive the PWM switch model, which is used to derive the small signal model of converter power stage, and with that we can formulate the small signal model of entire power stage. But for that case, we only discussed the CCM operation of the converter. That was the initial assumption for the modeling. But usually the converter operation spans both CCM and the DCM operation. So in this lecture, we'd like to investigate the DCM dynamics of PWM switch, and eventually we'll derive the DCM PWM switch model. First, we review the previous lecture. So for example, this is the buck boost converter. So this is called PWM switch, and this is active terminal, and this is passive terminal, and this is the common terminal connect to the capacitor. And then the voltage between active and passive terminals is denoted as VAP. Is this one is VS, and the voltage is reversed here. So VAP is VS plus VO. Okay, so that is the inherent characteristic of buck boost converter, and this is the small signal model of buck boost converter derived from this circuit diagram with this PWM switch. Simply we replace the PWM switch model with this PWM switch by pin-to-pin replacement. So A goes here, P goes here, and this C is connected to here. Initially this one was VAP, DC voltage across this A and B terminal, which is VS plus VO for this case of buck boost converter. So we have VS plus VO in the numerator, and we have D, stage state ratio D here, and this is IL. Originally this was IC, so IC is defined as the current leaving from this common terminal. So that becomes the inductor current for this buck boost converter. So IL is here, and this is replaced with this transformer, ideal transformer, with turns ratio of 1 to D, and this is the common terminal connected to the inductor. As I said in the previous lecture, so this is the common terminal connected to this inductor, and the D appears here, right? Because originally it was 1 to D in the original model of PWM switch. So this is called the CCM PWM switch model. This is the entire small signal model of a power stage. We want to extend this kind of analysis to the converter in the DCM operation. So we need the different formulation for the DCM operation, and the waveforms and the average education and the small signal education will be different from those of CCM. So I want just to show the glimpse of the upcoming lecture. So this is the conclusion of upcoming lecture. So here we have DCM small signal model, which is counterpart of this CCM PWM switch model. Okay, so this is the DCM PWM switch model. So it's a little complicated, and there's no transformer compared to the CCM counterpart. And we have 5 parameters. And this is the dependent current source, another dependent current source, another dependent current source. Okay, and we have 2 resistors here, resistive parameters, one here, another one here. So this is the DCM PWM switch model embedded in the structure of this buck boost converter. So this is the small signal power stage model of buck boost converter in DCM operation. the big difference between this and this is there is no transformer, and we have 3 dependent current source and 2 resistive parameters. And these are values of the coefficient of this dependent current source or voltage dependent current source, and 2 resistive parameters. This is the example of typical low power buck boost converter example. So at this particular example, you will see the details about this example. This Ri is 63 ohm, which is relatively large, and this Ro is 20 ohm, very large. Compared to other parameters, they are very small compared with this, and Ri and Ro is very large compared with other parameters. And this is the second order model because we have L and C, but with this large Ri and Ro will provide a strong damping to the dynamics that result in the Q quality factor of less than 0.5, much smaller than 0.5. That means if you have, basically you have quadratic term, but this quality factor becomes less than 0.5, that double pole will split into 2 dual poles like this with equal space in log scale. So result of this is split of double pole into 2 dual poles. This is the basic difference between this model, and this characteristic governs the dynamics of PWM converters in the DCM operation, which is very different from those of CCM operation. For example, this is duty ratio to output transfer function of some PWM converter. Any converter has the similar characteristics. This purple color was the CCM characteristics. So in CCM, for buck converter, you have DC gain of Vs, and we have double pole at the double pole frequency formed by this L and C. Okay, so this omega naught is here. This is the CCM case. But in the DCM, Q value of this double pole becomes less than 0.5. That means one pole goes this direction and the other pole goes this direction, and they split into one to the higher frequency, one to the lower frequency with equal distance in log scale. So distance between here to there should be same as the distance between here to there. It looks different, but they should be the same. Okay, so in DCM, you have this kind of duty ratio to output transfer function. You have some DC gain here, and this first one, which is split from this double pole, is omega 1 appears here, and this frequency is given by this 2 divided by C times R. So this is relatively small because this is large, C is large, R is large. Okay. And the other pole moves to the higher frequencies, and the exact location of this is very complicated, but usually this frequency is larger than this frequency. This is the half switching frequency. So usually it goes out of picture to the higher frequencies. So then you are interested in the low frequency and the mid frequency. This is the first order system. Okay. In particular, the expression of duty ratio to output transfer function in CCM is this one. This is RHP 0 and omega ESR 0 is in the numerator. They remain the same in both cases, but this is the denominator. This is a quadratic function, so it has double pole and the Q value of larger than 0.5. So it is double pole, but in DCM, the numerator remains the same, but the denominator is separate into 2 dual poles with much reduced quality factor due to strong damping effect of this large resistance value to large resistance value. Is the typical characteristic of this small signal model of converter, all the PWM converters in DCM operation. Right? So in the following lecture, we'll discuss the details about this. Okay? The derivation of this will be explained in detail, and we'll investigate the impact of change in this power state dynamics in DCM operation. So impact of this to the loop gain, output impedance, and transient, load transient response, and any other closed loop performance will be further investigated based on this result. Okay? This is the second part of this lecture. In this part, we'll discuss the PWM switch model in DCM operation or DCM dynamics of the PWM switch. Okay. So this is the buck boost converter. This is the circuit description, and this is the representation using this PWM switch model. So you are using this buck boost converter as an example to derive all the equations, because this converter is most convenient to use for this purpose, but result can be extended to the other two converters, boost and buck boost converter. Boost and buck converter, or any other buck converter, any other PWM converters. So this is circuit diagram, and this is IA. Somehow A is gone. IA. This is the switch current, active switch current, and this is IP is passive switch current, and this IC is common terminal current, which is same as the inductor current always. And this is the description of the circuit using the same notation. And this is the voltage across AC terminal and the voltage across the CP terminal. Polarity is different because the common terminal is in the bottom for the buck boost converter. Okay, and this is the waveform, DCM waveforms. This purple color is IC, which is inductor current. So this is the inductor current. And on time part of inductor current becomes switch current, IA, this IA, and this part is diode current, IP, passive switch current, and here the inductor current becomes 0 and remains 0 thereafter. So this is DCM operation, and we used this D1 in the past to specify the uptime period in which inductor current is existing. Okay, so we use the same notation, and we use this to derive the PWM switch model in DCM operation. So we are using buck boost converter to derive this, but this result is invariant. Okay, can be applied to all the PWM converters. Right, okay. So this is the analysis. This looks complicated, but idea is very simple. This is the IA, IP, VAC, and VCP plus minus. Somehow we want to derive the relationship between them in the average sense. Okay. So average is very important. First, we derive the average equation for this. If we obtain the average equation, remaining part is just linearization, which is mechanical procedure. Okay, can be complicated, but theoretically they are all the same. Okay, so but most important thing is voltage across this inductor VL is 0 in average sense because of volt-second balance condition for inductor. Otherwise, inductor will be saturated. Okay, in the average sense, this voltage is 0. Then, in the average sense, voltage across AC is this one, right? Because this is 0, right? In the average sense, voltage across this CP is this one, because this is 0 in the average sense. That is very critical. Okay, so this is not easy to understand. From his original paper, I spent some time to figure this out long time ago. Right. So now you know everything. So first IAT, IA bar T. This is the IA bar. It's just you average this triangle, obtain this area, and divide that by this switching period, which is this. Then this is cancelled, and you have this equation. And the IP is this one. Then you have this equation. In IA, D is here, and in IP, D1 is here. This is obvious, right? Because this is the DTS as this is D1 TS, right? Then with this, you have this relationship. Okay, you delete this, you eliminate this IL peak, then you have this equation. This is a current equation in the average sense. Okay, and the voltage equation, IL peak is given by this equation. This is voltage across inductor divided by L, and this period, this IL peak. Okay, IL peak is related with, this is the VAC bar, right? Because the average value of VL is 0, then this VS is same as this one. Okay, the key idea is this one. This VS is VAC bar. Okay, VO is this one VCP bar because of this, right? Then from this you have this equation. I wrote down here because this voltage is VS because this is 0. All right. Then you have this equation, this current equation, and the voltage equation. So you have two equations, and we have D1 here. This should be eliminated somehow. Then this is equation number 1. These two equations are numbered as 1, and these two equations are numbered by 2. And by solving this, you have expression of the D1. Okay, this one, which is same as this one. So you have 3 equations, 1, 2, 3. So these 2 equations specify the relationship between this current, this voltage in average sense, right? So that is the average equation of this, and the D1, it contains D1, so you have expression for D1. So you have everything, right? So next step is shown here. I repeated these waveforms somehow, and average equation, we use the notation of this mu is D divided by D1, okay? And the D1 is given by this equation number 3. You solve this equation together, and you will easily get this, which is tedious, okay? Then, so D1 is known. Then this ratio, this mu is this one, okay? So you have average equation of everything. So you have this simple equation, and this is given by this, and this is known. Then you linearize this equation, okay? This is very painful job, very tedious job. And Barche-Boperian, he went through this, and he concluded this. Then the linearization of average equation is expressed in this manner. So IA is determined by VAC and DT times some constant, and this one has 3 components, okay? And these values are given by this. This is Ri, Ki, Gf, Ko, Ro. The dimension of this is resistance. The dimension is resistance. And this one is what? This one is current, and this one is conductance. Okay, so this is the equation, and we have 5 variables here: 1, 2, 3, 4, 5, 6. Okay, but this one is very important. They are resistive parameters, and resistive parameter provide what? Damping. Okay, so I wrote down this, that here 2 resistive parameters, 1 and 2, provide A, strong damping. Okay, so in CCM, everything is a second order system. In DCM, if you have very strong damping, then Q value becomes smaller than 0.5. Then double pole split into 2 dual poles. All right. So the equation of this is this one. This is the circuit representation of this. This is very easy to figure out. Okay, so IAT is this one plus this plus this one, and IPT has 3 terms. Okay, this is the circuit model for the averaged equation of this, but this has small value. It does not have much value until linearized. Okay, then linearize this. Oh, it's already linearized. All right, let me take my word back. It has less value until transfer function is derived from this circuit model or this equation. Okay, but this is easier to deal with. The same thing, but to derive transfer function, we use this, and Popperian used this, and transfer function is shown here. Okay, so let me give you one numerical example for this. So this is the buck boost converter, right? And this IS switch current is the same as IA, and this is a parameter for this specific example. And switching frequency was 50 kilohertz, and the steady state duty ratio is 0.25. And with this parameter R critical, which determines the operational mode of converter, CCM or DCM, as this one. So this one is much larger than this. So this converter is in DCM. Okay, and IS, this output can be determined. This one is determined by the gain equation of input-output voltage gain equation of buck boost converter in DCM. We derived this long time ago. Using that, you derive this, and you obtain this using the power balance in this input and output, because we know the out voltage here, and this current is known because R is determined. Then this known, then IS is determined because the product of these two are same, should be same as the product of these two variables. With that, you determine this. Okay. Once these values are determined, you evaluate this. Okay. All right. Just numerical evaluation. Then value, final result is this one. All right. R1 is this one. Ri is this one, not one. Ri. Okay. Excuse me, this should be I. It's very large, right? And RO, this one, is very large too. Okay? This is the small signal model of this converter, right? And from this converter, you can derive all the transfer functions from the input to output, load current to output, or duty ratio to output. Okay? It's not easy to derive this, but that is possible. Okay? Then you plug this. Okay. This is the equation of, you need some approximation for this. Maybe you want some details, go to his paper. Then control to output transfer function. No, duty ratio to output transfer function is given by this one. Very similar to the CCM case. It has RHP0 and ESR0, but here this is split. Okay, there is no quadratic function, and we have two real poles. The double pole is split into two real poles, omega P1 and omega P2, and omega P1 is given by this 2 divided by C times R. This is large, right? C is large, R is large. So this occurs at very low frequencies, and omega P2, the exact expression of omega P2 is very complicated, but it can be proved that, and this is larger than half the switching frequency. Okay, so originally the double pole was somewhere here in the CCM case, and it's split into two real poles. So it's split two real poles, maintaining the same distance. Okay, what I mean is, all right, so it's split here, then the omega naught was here, and distance between this and this should be the same. Okay, I explained this once. Okay, splitting across symmetrically. So, all right, take a look at this. There is just some interesting, very important information is here. Okay, so omega P1 is this one. So it occurs at very low frequency, right? And omega RHP is somewhere here, and this one is omega P2 is far from here at very high frequency. Probably omega ESR, of course, somewhere here. So omega ESR is here, and this phase will be increasing at this omega ESR. Okay, it's not so at high frequency behavior is something similar to this. But the frequency is so high, so probably the modeling approach is not valid at these high frequencies. So forget about this one. So we are interested in this region. Then this is what? This is a first order system. Okay? Because there is only one pole here, and below this frequency range, in this range, this system becomes a first order system. There is only one pole. And this pole, this dominant pole, occurs at low frequencies, so the system dynamics will be very slow. Right? I think I mentioned several times in DCM, the dynamics are very slow. Because of this omega P1 dominate the dynamics of this power stage, and everything becomes this first order system with very long, large time constant. Okay, that is the reason for this. Let me show. Okay, we'll discuss I just introduced this page, and we'll discuss this in detail in the next Tuesday. So I showed these parameters of this buck boost converter, and with different value of the R. This R is 1 ohm, and this smaller, then DCM. So no, CCM. So this is a CCM. CCM has this double pole frequency at square root to LC is omega naught. Okay, and with this larger values of this double pole is split into two dual poles. So it's split. And this distance should be the same. So it looks different, but should be the same. Equally separated, split it in DCM operation. And take a look at the phase. This is the CCM phase. This is the CCM phase. Because there's the overload phase change, because it's second order system, quadratic term, phase is dropping by 180 degree at this frequency. But this is the DCM. There is only one single pole, so phase is decreasing by 90 degree. Okay, so it's obvious. This behaves as a first order system. Okay, another one is because of the splitting, this gain, this part is much reduced. This much. Okay, so this character is different. So I made some table. Understanding this is very important to understand the dynamics of converter in DCM, which are very different than those of converter in CCM. Okay, we come back to this slide in the next Tuesday, right? Okay. All right. So that's it for today. Okay. Thank you.